right, this is lesson 2.2 of our probability unit, and this is on counting outcomes. So we're just going to look a little bit more closely at some techniques you can use for counting possible outcomes and also possible ways an event can occur. So we're just going to look at some examples, basically. Our first example is, say we're choosing an outfit from 4 shirts, 3 pairs of pants, and 2 pairs of shoes. How many different outfits are possible? So this is asking how many different outcomes are there. So basically the idea is we're going to take how many options are there for shirts, multiply that by how many options there are for pants, because each of our shirts can be paired with each of the pants, and then multiply that by the number of options for shoes, because each of our shirt-pant combos can be paired with each of the shoes. So basically, let's see, we had 4 shirts, we had 3 pairs of pants, and we had 2 pairs of shoes. So the total is 4 times 3 times 2, which is 24. So 24 outfits. And the key insight here is you're going to multiply by the number of choices at each step. So that's our key idea. Okay, so now let's look at another example where we will do a probability. So in Minnesota, cars have license plates, and just, the basic normal license plate has 3 letters and 3 digits, 0 to 9. So first let's just say, okay, how many different license plates are possible? So letters, there are 26 possible letters, right? So if we allow that a letter could be used more than once, which can happen on license plates, for this, these are the letters. And we have 26 options for each of the letters. So 26, 26, 26. Okay, and now here are the numbers. So how many digits can we choose from? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 options. And if we allow that a number could be used more than once, which can happen on license plates, we would have 10 options, 10 options, 10 options. Okay, that's a lot. 26 times 26 times 26 times 10 times 10 times 10. Okay, yikes. So we get 17,576,000 different plates. That's a lot, and that's good because there's probably lots and lots of cars in Minnesota that need license plates. Okay, so that's the total number of license plates. It's basically like the total number of possible outcomes. Now let's talk about a particular event, or like a subgroup of these. So what's the probability that a license plate, a randomly selected license plate, has no repeated letters or numbers? Okay, so we know the total number of plates. We now just need to figure out how many plates are there with no repetition. Okay, so again, our first 3 spaces, those are the letters. And our last 3 spaces, those are the numbers. But this time we're not allowing repetition. So our first letter, we have 26 choices. But now we have to throw out a letter. So say the first letter was D. Now we can't use D in either of our other letter spots. So when I go to pick the second letter, I don't have 26 options, I only have 25. Because I can't use the letter that I had in spot 1. Okay, and then when I go to the third position, I've thrown out 2 letters because I can't use this letter anymore and I can't use this letter anymore. So now I only have 24 letters to choose from. Okay, with the numbers, we start off with 10 options, but then whatever number's in the first position, I can't use it again. So then I only have 9 for the second number. And then for the third number, we only have 8 choices. Okay, so 26 times 25, whoops. Okay, so this is 11,232,000. Okay, so now this is the number of ways our event can occur. This is the total number of outcomes. To find the probability, we divide them, right? Our probability is going to be 11,232,000 divided by our big 17,576,000. It's fine to leave your probability like that. If you want to make it a decimal, you can, and do the division. Okay, and you're going to have to round it, so it would be about equal to 0.64. So a little bit more than half. So it's more likely than not that there's no repetition, but not by very much. Okay, and again, the main idea here is that you're multiplying by the number of choices you have at each step. And in this case, the number of choices that were remaining at each step were changing because once we had used a letter here, we couldn't use it again. So the number of letters available to us was going down as we moved from position to position. Okay, I have one more example for us. So let's say we have 7 flute players and they're performing in a concert. Okay, the names of the players are going to be listed on the program in a random order. What is the probability that they are listed alphabetically? Okay, so we need to know the total number of possible orderings, and then we need to know the total number of ways they could be listed alphabetically. So total number of possible orders. There's 7 flute players. So for the first name, we have 7 options. But then we're not going to relist that same flute player. So for the second position, we only have 6 options. And then 5, 4, 3, 2, 1. Okay, so that gives us 5,040 possible orderings. Okay, now we want to know how many ways can they be listed alphabetically? Well, there's only one way to list a group of names alphabetically. So our probability is going to be one way out of 5,040 total ways, which is really small. So I'm going to leave it as 1 over 5,040. Okay. And again, we were multiplying by the number of names available to us at each step. So this was the choices for the first name, this was the choices for the second name, this was the choices for the third name, and so on. Okay, now let's say there are 4 chairs available backstage for the players to rest in whenever they're backstage. If all the 7 players are there, how many different seating arrangements are possible? Okay, so this is the first chair, this is the second chair, and so on. So we've got 7 people, so there are 7 choices for who sits in the first chair. Then once that person sits down, there's 6 choices for who sits in the second, 5 for who sits in the third, and 4 who sits in the fourth. So the total number of seating arrangements is 7 times 6 times 5 times 4, which is 840. Okay. Now let's say Isa and Alex are 2 of the players. What is the probability that they sit in the first 2 seats? So let's say Isa is I, and Alex is A. So they have to be the first two seats. Okay, so maybe Isa is in the first seat and Alex is in the second seat. How many choices do we have for the third seat? Well, there's 7 total. Isa and Alex are out because they're already sitting down. So there's 5 people left. So there's 5 choices and then 4. So that's 20, where it goes Isa, Alex. But maybe Alex was first. It didn't say who was first, it just said that the first 2 seats have to be Isa and Alex. So it could be Isa, Alex, but it also could be Alex, Isa. So now if it's Alex, Isa, then they're out, and then we have 5 choices and then 4 choices for the remaining seats. So we have another 20. So altogether there are 40 ways that Alex and Isa could be in the first 2 chairs. Okay, so then our probability is going to be 40, that's the number of ways this can happen, divided by the total number of arrangements, which is 840. And that's not so small, so that's about equal to 0.048. That's pretty small. So it's not likely that that's going to happen. Okay, so that's some examples of how you can use counting principles to count possible outcomes and to count the number of ways an event can occur. And the main idea here was to multiply by the number of choices available to you at each step.